Huh?
What's going
What?
on? One is 14, one is 20. How can you still prove that the distance is absolute?
What do you? Oh, that's
So,
what you.
do you
Okay,
want? Yeah.
wait. Uh,
Okay.
20 meters is the distance between observer A and an object. 14 meters is the distance between observer B and an object. No one was ever claiming that these two would be the same. What matters is that observer.
This is Rashibari from Columbia University. Welcome to Daily Physics. Today, episode 12. Today, our topic is Galilean Transformation. I myself going to give you a good understanding, but I'm going to keep it high school level. However, I invited two students. Isaac is from NYU. He's going to give you an undergraduate level understanding. Welcome, Isaac.
Salutations.
And Raf, he is from Brown University. He's going to give you a graduate level understanding. Welcome, Raf.
Hello.
All right, consider two students, Zoe and Mo. Is x and y, and Mo's reference is also x prime and y prime. Call this one s prime. Now put them together. If I put them together, this one is x, this one is y, this one is s, and this one is x prime, this one is y prime, and this one is s prime, right? At point P, here, point P is how much distance away from Zoe?
I can't tell.
X.
X distance away, that's right. And point P defined by what? X, comma, y, z, comma, t. And point P prime is
X prime, Y prime, Z
X
prime,
prime, Y prime, Z prime, and T prime. Now, this is Zoe, and this is Mo. Now, for Mo, the X prime would be what?
X prime.
X minus what?
VT.
X minus VT.
Y prime is?
Moved in the x direction, so we only consider.
Okay. What about Zoe?
And
X is?
X prime is x is x.
Y is Y.
Z is?
V is Z. And T is T.
But we know everything about Zoe, right? And now Zoe is at rest, of course, right? Now Joe throw a ball with 10 meters per second. How can we write it?
Joe throws the ball at 10 meters per second this way, in the x direction.
And now V is, you're going to say V is 3 meters per second. What does that mean?
Hey, but isn't the velocity 10 according to your equation?
I can put U. What does that mean? U is 3 meters per second. Mo
is Joe moving at 3 meters per second?
Mo is moving 3 meters per second with respect to?
Can you just write VMO next time? With respect to Joe?
With respect to Joe. So Zoe C, Mo is moving 3 meters per second. But for Mo as for reference, Mo is not moving.
Okay.
Is that
right? So who is the ball moving 10 meters per second with respect to?
What's that?
Joe.
Joe throw a ball horizontally.
Okay.
Zoe throw a ball, so I'm gonna say.
Oh, I see. Okay.
Zoe throw
a ball. Okay.
Throw a ball at x direction.
Okay.
And at t is equal to 0. At t is equal to 0, P is equal to P prime.
Okay.
Right?
Yeah.
Yes.
At t is equal to 2, P is not equal to P prime. What is what?
Yes.
Okay.
I'm right here. I've always been right here.
Okay, good. Now, we gotta try to find the distance. Okay, so distance of the ball after 2 seconds would be what? P of 2 for Zoe is how much?
20 meters.
2, which is 20 meters.
What?
P of Mo of T is equal to what? P of Joe minus minus what? UT. Is that right?
Okay.
So that P of Mo after 2 seconds is P of Joe is
20
minus U is
minus 3T.
So P of Mo is 16. Is it 16? No, 14.
No, 14. Okay, so Joe is moving 3 meters per second with respect to Mo.
So what happening is Zo gonna move, Mo gonna move, right?
Okay.
You see the velocity is not 10 meter per second, is less than 10 meter per second. Why is that?
Okay.
Because the ball is
Oh,
moving
okay,
in the same
okay.
direction, Mo is moving.
Okay, okay,
So
okay.
Mo sees it at 7 meters per
If
second,
Mo was moving
I
at 10
see.
meter per second, the ball would be
Not
right
moving.
above him all the
Not moving.
times.
yes,
Not moving. Yeah, yeah, yeah.
not moving at all. Okay, so this is a high school level. So I teach high school physics here in the university. So I give you folks out there who are high school students. Okay, I solve their need. Now, Isaac, your job is to solve the need for undergraduate students.
Okay, so we're back to undergraduate physics class, I guess. You can see this?
Yeah.
Okay. So the Galilean transform is how we define essentially the concept of reference frames in classical mechanics. So it's pretty simple to understand. Let's say I am going to throw a ball upward and rightward. And let's say its horizontal velocity is 10 meters per second. Then my son, don't question how I have a son at 13 years old, it's not relevant, is running at the exact same velocity. Don't question how he can run at 10 meters per second, that's just how he does his thing. And what's going to happen? Well, you're going to observe that the whole time, my little son is going to have the ball directly above him because their position functions are going to be exactly the same. Therefore, if little Jimmy always looks up, don't question why he has a singular eye and it's this deep inside his head. That's just how.
I'm sorry. You throw the ball at what velocity?
He will believe 10 and my son is running at 10. It doesn't really matter what the velocity is as long as those two are the same. Because these two fellas have the same exact horizontal.
You throw the ball at what direction at 10 meters per second?
Well, its horizontal component is 10 meters per second.
Why did
the
you
vertical
drop,
component is?
Why did you draw vertical component?
What the vertical component is isn't relevant right now.
So erase it. It confused me. I'm an undergraduate student.
Sure. I don't know. Let's call it 5 meters per second. But we're never going to use this again. So, what happens now? Well, little Jimmy, if he looks upward, is always going to see the ball directly above him. To him, it's not going to be moving in the horizontal direction because both of them are going to have the same horizontal position function. So, it looks like little Jimmy will say, "Hey, did you really throw the ball? I saw it moving at 0 meters per second in the horizontal direction. I only saw it moving vertically." So that's what the concept of reference frames is all about. If something is moving in the same direction as you, then you are not going to observe it with the same velocity as an outsider might say. So, for instance, if your car is moving at 30 meters per second and another car is definitely breaking the speed limit and moving at a whopping 60 meters per second, it makes sense that they would overtake you, right? But what velocity are you going to see them moving at? Well, and of course, what does 30 meters per second and 60 meters per second actually mean in this context? It means with respect to the road. You can't ever specify a velocity without specifying what reference frame something is in first. So, how will you observe the car that's definitely speeding? Well, of course, when you're in your car driving, you don't see the components of the car. You don't see the steering wheel steadily moving away from your hands. You don't see any parts of the car drifting away from you. The entire car is moving at the same speed as you. It often seems like the car is not moving at all. You can't tell the difference between whether the car is moving or the car is at rest. Of course, unless you look outside the window. But who wants to do that? So, you think you are moving at 0 meters per second. And so naturally...
Isaac, finish it quickly and with the diagram. The main point is we already talked about reference frame, but this is Galilean transformation with the diagram.
All right. So, what are you going to observe about the speeding guy? Well, in 1 second, he's going to travel 30 meters farther than you are. So you're going to observe him moving at 30 meters per second if you think to yourself that you're moving at 0 meters per second. Now, how do we formalize this? Since this is very vague, well, that's through the Galilean transform. The Galilean transform tells us how exactly, if we're given the specific information as to how one observer sees an object, then using the position and velocity of this observer and the position and velocity of the other observer, we can deduce what the other observer is going to say. Newtonian mechanics, time is absolute, so we don't have to worry about forming, but position is the more important part. If you have the three position vectors, let's call x, y, and z the position vectors that observer number 1 uses, and x prime, y prime, z prime the coordinate system that observer 2 uses. You can transform between them by saying, well, x prime is just equal to x, the original observer, minus v, which is the velocity of the original observer when compared to the new observer, multiplied by t, where t is, how much time we're observing this interval over. How long the interval is. And the same thing happens for the other two coordinate frames. In fact, you might as well just write r prime is equal to r minus t multiplied by v. This is the Galilean transform at its core. And of course,
wow.
if you really wanted to, you can write t is equal to t, but that's useless.
Okay. So Ref, can you don't move away too much from the problem I solved.
Okay.
Okay. Go ahead.
That was a great explanation, Shiba.
Skippity.
So let me draw the. So what I'll do is I can give like a little bit more graduate level understanding of the Galilean transformation, but the basic idea is still the same.
You're gonna use the same problem, baby.
Yeah. Okay. So let's say this is x, this is t, x prime, t prime. Okay, so far so good.
Why t? Why not y?
Yeah, we can call it y. This is
not
meant to be more like
this is not Lorentz transformation yet.
Okay, I can keep it x and y. Okay, so and let's say that this is Mo's reference frame, okay, and this is Joe's reference frame, and Mo is moving with some velocity v with respect to Joe, and Mo and they're both trying to describe the location of an object. Okay, so for let's see. So in an amount of time t, the distance between Mo and Joe is going to be vt, right? And we know that in Joe's reference frame, the x coordinate of this event is just x, right? So that means in Mo's coordinate, x prime will just be x minus this amount, vt. And then there is no movement in the y coordinate or z coordinate or t coordinate. So they all stay the same. So these are the exact same equations Dad wrote down. Right? So the only thing that I can do now is there's a simple way you can write this as a matrix. That's the only difference that happens between the graduate and undergraduate version of the Galilean transformations. So the matrix form is very simple. You replace the left-hand side here with just a vector, and the vector has these components, x prime, y prime, z prime, t prime, and this is equal to the original position vector x, y, z, t, and then minus we have the velocity vector. So this is v x, v y, v z, 0 times t. Now, can you still see what I? Okay, so in this case, there is no vy, there is no vz. So this is just 0, 0. So this is
yeah,
just,
notice that's basically just what I wrote.
yeah. So this is just another way. Now, oftentimes you just write this the r prime vector. This is equal to the r vector minus vt. So this is just another way to write. So let me bring this over here. R prime is r minus vt. But this is just another way to write the kinematic equation. The final position is the initial position minus vt, right? Mm-hmm. So this is just another way to write the kinematic equations. And now if you take the derivative of both sides, what do you get? The derivative of position is velocity, derivative of initial position is initial velocity, and then derivative of velocity is acceleration. Okay, so you get something very similar to VF is VI plus AT, except the only reason you have a minus sign here, not plus sign, is because this reference frame, Mo's reference frame, is moving in this direction to the right with respect to Joe. If he was moving in the other way, then this would be exactly the old kinematic equation, VF is VI plus AT. So yeah, that's the only.
So find it. One answer is 20, one answer is 14.
One
answer is 20, one answer is 14.
What is 20? When
the ball is 20 meters away from Zoe and ball is 14.
Okay, yeah. So we can do that. So, okay, so.
And visually show that my ball is 20 meters away from Zoe and 14 meters away from Mo.
Okay, so Mo is traveling at 3 meters per second to the right with respect to Joe, and the ball is traveling at 10 meters per second with respect to Mo. With respect to Joe, sorry. Okay, so let me write it like this. Velocity of the ball with respect to Joe is 10 meters per second. But the velocity of the ball with respect to Mo is going to be less than 10.
7.
It's going to be 7 because Mo is traveling 3 meters per second this way. So it's going to be 7 meters per second. So that means after 2 minutes, Mo will say that the ball has traveled to 7 times 2, which is 14 meters. But Joe will say that the ball has traveled to 20 meters. And why? It's because Mo has already moved 6 meters in that 2 minutes. So this...
In that 2 seconds.
In 2 seconds. 2 seconds, yeah. So this is why Mo says the position is 14 meters. Joe says it's 20 meters. Because in that 2 seconds, Mo moved 6 meters.
So, all right. So being everybody back, and according to is Newtonian mechanics, the distance is absolute. So, but in this case, we don't see distance is absolute. One is 20, one is 14. What's going on, Isaac?
Huh?
What's going on? One is 14, one is 20. Can you still prove that the distance is absolute?
What do you? Oh. That's what you. Okay, wait.
Okay.
20 meters is the distance between observer A and an object. 14 meters is the distance between observer B and an object. No one was ever claiming that these two would be the same. What matters is that observer B will see the distance between observer A and the object is the same, and observer A is going to see the distance between observer B and the object is the same as observer B would. So 20 meters is the distance between Joe and the ball. 14 meters is the distance between Mo and the ball. That is not what we are claiming when we say distance is absolute.
Okay. Raf?
We are wait, no. All we're saying is that the distance between A and B never changes with reference frame. We did not specify the distance between A and C and the distance between B and C